I would like to say something about Newton, who was a great scientist and he made great distributions in both physics and mathematics. He was well aware of some difficulties of physics, mainly in the instantaneous action at a distance and the wave-particle duality of light. Unfortunately, at Newton's time, men believed themselves to be the center of creation, both physically and spiritually, and he was obliged to abandon whatever bold theory had in mind because he knew it would be rejected as absurd. He missed paving the way for the two great theories of 20th century, the special relativity and the quantum mechanics. Uh, the well-known Galilean transformation of two inertial frames um, with a relative velocity between them, let's say v, is as follows. G prime equals t and x prime equals minus v times t plus x. And in matrix notation, we have this expression, and the inverse Galilean transformation will be as follows. T equals t prime and x equals v times t plus x prime. And the corresponding matrix notation is this one, with the matrix, the 2 times 2 matrix is with plus sign. Now, in order to symmetrization of this Galilean transformation, we have to put an extra minus v on the upper right corner of this matrix, but now this expression is meaningless because we have mixed time and length together. So we have to make this expression either in dimensions of length or in time. So we have, in case of dimensions of length, we have to put an extra c, where c is a velocity, whatever it is, this velocity. So you have c times t prime, and this is now expressed in length here and here, and this matrix must be dimensionless, so you have to divide the velocity v in both these two places with the unknown velocity c. The same applies to time, but we are going to work with the length, the dimensions of length. Now, we have also to put a scaling factor gamma to this expression, and we have now the expression for the dimensions of length, this one, and if we replace the fraction v over c by the Greek letter beta, we have this expression. And now, finally, we we found the Lorentz transformation, which is the matrix L equals gamma, gamma here, minus gamma beta here, and the inverse Lorentz transformation is with the plus sign. The product of Lorentz and the inverse Lorentz transformation is equal to 1, and from here you have the famous relations of gamma equals 1 over square root of 1 minus beta square, where beta equals the fraction v over c. All we have to do is, in order to find the Lorentz transformation, is to postulate an upper bound of propagation of action. And this implies that it is constant in every inertial frame, and that there is no privileged observer. So Newton, he theorized the existence of an unseen force capable of acting instantly across great distances, introducing a mysterious influences. Otherwise, he had to concede the action occurs at a certain velocity, let's denote it as c, representing the maximum speed at which information can propagate, that remains consistent for all inertial observers, regardless of their relative velocity. If this were not the case, we could have varying velocity of transmission, such as c plus v, potentially leading to instantaneous action at a distance. Consequently, the c cannot conform to the Galilean transformation. These assumptions alters the cherished concept of absolute space, which becomes contracted, and time, which is dilated, to maintain a constant rate of information propagation for all observers. Ultimately, Newton overlooked the chance to lay the groundwork of special relativity. The special relativity is based on two principles only. There are no privileged observers, and the propagation of light, the information, is the same in all universal frame. There is an upper bound. Newton's law of motion obeyed the first principle, and as for the second, Newton was almost there. But Newton also made a great distribution to quantum mechanics, and it is considered as the first quantum physicist. While Newton missed the chance to lay the groundwork for the 20th century special relativity, he was nonetheless a trailblazer in the field of quantum mechanics. In his work Optics, he observed that light exhibits both particle and wave characteristics, and he sought to unify these two concepts. Unfortunately, his idea went largely unacknowledged, and later physicists predominantly supported a solely wave-based interpretation of light. Thank you very much.